what an extraordinary result. So basically in front of me in the screen you can see that we are integrating and summing up the binomial coefficients. And the sum is from 0 to infinity, that means positive or non-negative real numbers, and the integral is from entire real numbers, it's for entire real numbers. And surprisingly these two are actually equal. Yeah, so it's pretty mind-boggling to think about this result. But in this video, let's not go over the beauty, but over the rigorousness of the proof. How do we prove this result? Okay, so to prove this, let me first define the binomial coefficient for you. So binomial coefficient NR is defined as n factorial by r factorial n minus r factorial. You can also write this as n minus 1, and this is up to n minus r plus 1 by r factorial. Yeah, okay. So now let me show you some interesting stuffs. Like if you want to find n, choose n, that will just be n minus 1, and this goes up to n. In place of r we have n itself, n minus n plus 1 by, in place of r we have n factorial. So this is also n factorial by n factorial. So n choose n is 1. Now if I want to find n choose n minus 1, that will be n minus 1, and over here we will have n minus, sorry, let me I want to say n choose n plus 1, n minus n plus 1 plus 1, yeah, this is the last term, by n plus 1 factorial. Now this over here is actually 0, n minus 1 plus 1. So since this term is 0, the entire product will also be 0. Yeah, please note these stops. Similarly, if you want to find out n choose n plus 2, basically you will have all of these terms, n minus 1 and then n minus 2, and over here we will have 3, 2, 1, 0 as well as minus 1 as well. But since there is a 0 in the product, we can say that this result is also equal to 0. So from here what I actually want to say you is that when in this sum, in this infinite sum, in this infinite sum, when x is equal to n plus 1 or n plus 2 or any way bigger than n, in that case n choose x is just 0. So that's why we can say that this sum is actually equals to sum from x equals to 0 to n only of n choose x. And we know that sum of binomial coefficients from x equals to 0 to n, this is just 2 to the power n. And the short proof for this is from the definition of binomial expansion. We know that 1 plus x to the power n is sum from x equals to, or let's say since there's already a x, sum from k equals to 0 to n of nck x to the power n, and if we substitute x as 1, you get 2 to the power n is equals to sum from k equals to 0 to n of nck times 1 to the power n, which is 1. So you get the proof that the sum of binomial coefficients is actually 2 to the power n. So we have solved the discrete version, and that is 2 to the power n. Yeah. But now let's try to prove that this integral is also 2 to the power n. How do we do that? So for that, let me denote this integral by I of n. Let me denote this by I of n. The I of n is integral from minus infinity to infinity of n choose x dx. Okay. Now what can we do after this? Now what I can do is, basically if I let x as y plus 1, the integral still remains unchanged. So basically we will have integral from minus infinity to infinity, and choose y plus 1, and still there will be dy. And note that since this is a dummy variable, I can again write this as x. Yeah, can again write this as x. So these two are actually the equal integrals and denoted by I of n. So I can say that 2 times I of n is the sum of these two. And you might notice why I'm adding these two, because there is a formula for binomial coefficients where if I add these two stops, you actually get a similar thing, which is 2I of n is equals to integral from minus infinity to infinity n plus 1, choose x plus 1. You can prove this from the definition of the binomial coefficient itself. From this definition itself you can prove this result, and I leave that to you. Now again I've told that I can again replace x plus 1 by y, and the limits of integral remains unchanged, so I can write this as 2I of n is equals to integral from minus infinity to infinity of n plus 1 choose x dx. Okay, so this can be done, as I have already shown that here also I have changed the x to x plus 1, and that this is similar. Now we know that this is I of n plus 1. So now we have 2I of n is equals to I of n plus 1. This also implies that I of n is equals to 2 times I of n minus 1. Okay, now similarly we can proceed up to I of 0. This is 2 times I of n minus 2, so we have 2 square times I of n minus 2, and then 2 cube times I of n minus 3. So that's why we can write I of n as 2 to the power n times I of n minus n, which is 2 to the power n times I of 0. Now it's comparatively easier to find I of 0. That's why we reduced the problem to this case. Now to find I of 0, we know that I of 0 is just integral from minus infinity to infinity of 0 binomial x dx. Now we can use the definition of the binomial coefficient. This is 0 factorial by x factorial 0 minus x factorial. Yeah. Now after this, we know that in terms of gamma function, this is actually gamma of 1, this is actually gamma of x plus 1, this is gamma of 1 minus x. Now you see that here we can actually apply the reflection formula. So basically if we write gamma of x plus 1 as x times gamma of x, here we have gamma of 1 minus x. And we know that gamma of x and gamma of 1 minus x actually pair up to form the reflection formula. Yeah, that's why from the reflection formula I can say that this is actually equals to x times pi by sine pi x. And let me take sine pi x in the numerator, sine pi x dx. Okay, now if I let pi x as y, the limits of integral still remains unchanged. So this is sine y by y, and here we have dy by pi. And you might know that about the Dirichlet integral, which is famous all over the world, and it's also on YouTube as well. That integral from minus infinity to infinity of sine x by x dx, this is actually equal to what? This is actually equals to pi. So its proof are there on the internet and also on my own channel, and I will link the video over here. Now we know that this integral is actually equal to pi. Yeah, and pi by pi is 1. So this simplifies to 1. we see that I of 0 is actually 1. That's why I can say that this is 2 to the power n times 1, so that's 2 to the power n. Now, from both the sides, we got the result to be 2 to the power n. So that's why we have now rigorously proved that both of these results are 2 to the power n and they are same. Now I want to talk about the flow. We first change the discrete sum from x equals to 0 to infinity to from 0 to n because we saw that others are 0. Now this was an standard idea. And then for the integral we tried to use recurrence relation because we found that I of n is 2 times I of n minus 1, and then use the same property up to I of 0. I of 0 was easy to find using the reflection formula. So that was it. Hope you enjoyed the video. Thanks for watching and look forward to seeing you in the upcoming videos too. And keep enjoying mathematics.